Okay, we're recording now. So for the record, let me just go over this real quick. Our original differential equation was a population model where we said that the change in population was proportional to how much population we have. And that led to a differential equation, P prime equal Kp, which has a solution, P is equal to an arbitrary constant times e to the kt. And this differential equation and solution can work well for small segments of time in certain areas of the time continuum, but it's going to eventually grow exponentially, or if k is negative, it'll do an exponential decay and become asymptotic to the horizontal axis. That would be, if this is following a species, that actually would be the extinction of the species. So to modify that model in search of a model that is more realistic, we're going to define both birth rates and death rates that are not constant, that are functions of time. They can change over time. And then we've said, and we're trying to set up a differential equation here. So given a small segment of time, delta t, between t and t plus delta t, if beta of t is our birth rate per unit per time, then the number of births would be beta of t times the population at time t times how long we're watching delta t. Very similar for the deaths. And then we've concluded that the change in population would be people in minus people out, births minus deaths. And then that would be, excuse me, I'm getting all choked up here, getting emotional about the differential equation, I guess. This would be our delta P. If I would divide both sides by delta T, we would have a delta P over delta T is equal to PT. I guess I'll use parentheses here. Beta of T minus delta of T. And then if we would just look at this, delta P over delta T, if I take the limit as delta T goes to 0, that gives me, by definition, the differential equation, P prime T. So P prime of T would be P, which is itself a function of T, beta T minus delta T. I mean, nothing, I don't think, very profound there. This is called the general population equation. And if this is P prime. If beta and delta are constants, then the general population equation reduces to what we started with, because what would we have here? If these are constants, then their difference would just be K. And so we would have the original differential equation. But when it gets interesting is when beta and delta are not constant, and then we get something a bit new. So let's look at problem 10. Page 82 of our textbook. And it says, consider an impoundment of some kind that's got a population of fish. And there's a disease in this impoundment that's affecting the birth rate. And suppose that the beta of T becomes 0, and that the delta of T is equal to a K, a constant, over the square root of P. So we've got an impoundment, a population of fish. P of T would be how many fish are in that impoundment at time T. Because of a disease, the birth rate has gone to 0, and the death rate is proportional, or inversely proportional, we might say, to the square root of P. That is, delta T is a constant divided by the square root of the population. And we know a couple other things. We know that when T is equal to 0, the population P naught is equal to 900 fish. And we know that at a later time, that is 6 weeks into this study, the population has fallen to 441 fish. And then the big question is, when is the population equal to 0? I got a little crowded here, and so I wrote in a 0 instead of using the figure. So when is the population 0? When is this impoundment pond, tank, lake going to have no fish? So if we would call this equation right here, if we would call this A, then using A, we have dP dt is equal to P, and then this would be 0 minus K over the square root of P. And of course, I put the 0 in to remind us that the birth rate is 0 in this problem. So this is equal to, here's the negative, and I've got a P over the square root of P, which is just a root P. So this is negative K square root of P. So that's my original differential equation. Kind of ignore that. dP dt is K root P. So this is what kind of a differential equation? This is a first order, and its variables separable, because I'm going to be able to put all the P and the dP on the left-hand side and only the T and the dt on the right-hand side. Now, if we wanted to add more terminology here, it's also an ordinary, because there are no partial derivatives, so it's also an ordinary differential equation. And that's probably as much as we can classify it. And if you were asked what kind of a differential equation it was and you left off ordinary, I would not fault you for that. It's clear to everybody that that's an ordinary differential equation. Well, can we solve this ordinary differential equation? If I go ahead and algebraically separate the variables, I've got something that looks like P to the negative 1/2 dP is equal to negative K integral dt. And that will lead, forgot the integral there, that will lead you to P is equal to C minus KT over 2 squared. So this is your general So that's your general solution. Now the general solution will have, it was a first order differential equation, so it'll have one constant in it, and that would be our constant C. Now this is an initial value problem. We know that initially we had 900 fish in the pond. So we know that P of 0 would be the thing we call P sub 0, would be 900, and that would be C minus K, but our value of T is 0 at this initial condition, squared, like that. And this then is equal to C squared, and therefore C is the square root of 900 is 30. So our solution, our particular solution is P of T is equal to 30 minus K by 2T squared. And we can evaluate K also because we know that 400 and what was it? How many? 441. 441 is equal to P of 6, which would be 30 minus, now this is going to be T equals 6. So 6 over 2 would be a 3. So I'm just going to say 3K squared. And then, just another little algebra push. And we've got a K equals 0. Therefore, K is equal to 0. So the solution to the differential equation in particular is P of T is equal to 30. Why did I write K equals 0? K would be 3, not 0. So our particular solution would be 30 minus 3/2 T, the quantity squared. All right, so this is the particular solution. And then our question was, when is P of T equal to 0? Well, 30 minus 3/2 T squared equals 0 if and only if 30 minus 3/2 T is equal to 0. And this is easy enough to solve for T. And we find that therefore T is at least approximately equal to 20, about 20 weeks. So an example of a differential equation describing a population where we play with both the birth rate and the death rate. I've got something else I want to do this morning, so I'm going to give you just a hint at a video that I'll make probably later today or tomorrow morning, where we're going to make the birth rate a linear function instead of a constant. The birth rate, in this case, the birth rate was 0, a constant, but we can make the birth rate a linear function. We can make it any function we want to of time, but the first example we're going to look at is a linear function, and we're going to come up with something called the logistic equation, which says that P prime, the change in population, is a constant times P M minus P. And you can see right away that this is called a logistic equation. And it has this property. M will be a constant called the carrying capacity of the environment, or the limiting population. As the population gets closer and closer to M, this parentheses gets smaller and smaller, and we've got K and P now being drugged down by a fraction here that gets smaller and smaller, meaning that P prime of T is going to be decreasing in the normal course of things. And the equations would graph something like this. We'll let this be a time axis. And this can be a population axis. And just suppose that M fits in here, and we may start with a P0, little bitty population down here, but as time increases, my population will approach this limiting value, which would be like that. And as I approach it, my rate of growth is going to be decreasing, and I will then asymptotically follow my limit M. On the other hand, if I start with a population that's too big, I've got an island and I stock it with, okay, if I overstock the island initially, then my population would start up here, but my logistic curve would approach M again. These would be a die-off, this would be a population increase, and we stabilize around M. So I think it's not too hard to imagine that for many, many populations, that's a better description than anything we have so far. So we'll do that in a video and then talk again about population models. And we may be doing some velocity acceleration models depending upon how the population model goes. Today, I want to do something different. I promised you in the syllabus that we would occasionally have 5-minute quizzes, and I've just been busy or lazy, you fill in the blank there, and haven't given you any yet, but we're going to have one today. So I want you to find a piece of paper and write your name on the piece of paper, and you're going to take a 5-minute quiz and then upload it just like you upload homework to a place that should have appeared while we were talking in our coursework section on eRacer. So let me see if I can share the 5-minute quiz. Okay, Erica, can you see the quiz?
Yes, I can.
Okay, if you can see it, everybody can see it. So there's your quiz, and you got much more than 5 minutes to do it, but it's the first one, so I want to work kinks out. So you go ahead and work on the quiz, and I will I'll watch you work on the quiz.